Hello everyone, and welcome to today's chem lesson. Today we are going to spend some time talking about concentration, which is a way that we can numerically label solutions. Now we already have words to label our solutions with. We can call them unsaturated or saturated or supersaturated. Hey Michael, welcome back. And we already know that these words exist, right? We already know that we can call things saturated or unsaturated. But unsaturated, for example, can be any number of different things. And while it helps us narrow down our solution to what we're talking about, right, it doesn't give us anything super precise. If we think back to the video where we introduced saturated, unsaturated, supersaturated, we said that saturated meant 4 dissolved ions. And that means unsaturated can be 1, 2, or 3 dissolved ions. And that's 3 different things that would get the same name. And as we know, we don't want that. We don't like that. And so, depending on the situation, we have 3 different calculations we can do to assign numerical values to these solutions, to give them more specific names. Instead of just saying an unsaturated solution, we can say it's a 1 molar unsaturated solution or a 2 molar unsaturated solution, just to zoom in and identify and differentiate between these 3 different unsaturated solutions. And we're going to take a look at each of these things in turn. Molarity is our first one. Molarity is a measure of moles per liter. It's a measure of that ratio of moles of solute per liter of solution. The formula is on table T for you to pull up and look at whenever necessary. And this is the most common concentration calculation. When we take moles of solute over liters of solution, we get capital M, or molarity. When you're using it as a number, right, when you say 2m, you read that as 2 molar. And the calculations for this can be anywhere from pretty complicated, which is going to be our first one, to pretty simple, which is going to be our second one. For a more complicated molarity calculation, we are given grams of a compound and milliliters of a solution. And in this situation, we don't have moles and we don't have liters, so we have neither of the 2 units that we need. And so we're going to need to do some calculations. We know that there's 1,000 milliliters in 1 liter, and so to convert this 500 milliliters is a pretty simple moving of the decimal point. But for this 80 grams of sodium hydroxide, we have a couple of steps we need to take. First, we need to identify what sodium hydroxide is. Then we need to consult the periodic table to find the mass of each atom and add them together. And that's going to give us the mass of 1 mole. If 40 grams equals 1 mole, then 80 grams will equal 2 moles. And when I plug into my formula now, I have moles and I have liters. And I can plug in and solve to get 4 molar as my answer here. There were multiple steps and multiple calculations involved here. But as soon as we got moles and liters, we were able to plug in and solve. For the second problem, we have a little bit of a different setup. They tell you the molarity ahead of time, and they give you the amount of liters, and ask you to solve for how many moles there will be. Here, as long as you identified everything correctly and plugged it in, you're going to get your answer of 12 moles pretty easily. When we're talking about molarity, the units of your numerator and your denominator are the most important pieces. They must match up. Right? We can't plug 80 grams into this. It just won't do anything. We can't plug 500 milliliters into the denominator. It just won't do anything. We must make sure we get moles and liters before we solve. Our second calculation is going to be parts per million. Our parts per million formula is also on table T, available for you to pull out and look up whenever you need it. And in parts per million, what we're looking for is the mass of the solute divided by the mass of the solution. And here, like I said for molarity, it was the units that mattered most. Here, it's the context that matters most, solute and solution. Units don't really matter as long as they are the same. But when we're talking about solute and solution, we need to pay extra careful attention to what they are telling us. For example, 0.02 grams of sodium phosphate dissolved in 1 liter of water. When I go to plug this in to my parts per million equation, I can't just leave 1,000 as my denominator, because water is not the solution. Water is the solvent, and we know that solute and solvent together equal our solution. And so it's not just 1,000 in our denominator, it's actually 1,000 plus the solute. It makes a minor difference mathematically, but it is important to understand why we have to do this. If we get comfortable putting water in place of our solution, we are going to make a large number of mistakes. Sometimes those mistakes can be rounded away, right? If you had forgotten the 0.02 here, you would have gotten an even 20 parts per million as your answer. But with this 0.02 added in, it rounds a little bit down to 19.999. But if we get into this habit, this bad habit of saying water is the solution, which is not true, then we end up making that mistake in other places where it is a much bigger part, right? Like when we look at percent by mass in a minute. For the second problem, we actually end up with the exact same thing. We're going to take our 2 units. We have to make sure they're equal. Right here we have 40,000 grams of water and 0.000250 grams of uranium. Water is not the solution, so we need to include this in our denominator as well. We must add them together. And when we divide those and multiply them by 1,000,000, we are going to get 0.0625 parts per million. Right, the unit here is just an abbreviation of our process. Right, ppm for parts per million. And you'll notice that when we're using this, we have a teeny tiny amount of solute in a much bigger amount of solvent. This is used for testing things like water quality or air quality. Right, looking at how much dust there is parts per million in the air, how much uranium there is parts per million in the water, how much gold there is parts per million in the ocean. Right, this calculation is reserved for those situations where there's the teeny tiniest amount of something in a much bigger solution. And when we go to check our answers here, we're going to see that they line up pretty nicely, the 19,999 and the 0.0625. Right, exactly where we expected them to be. Our last calculation, percent by mass, is very similar to parts per million. It's actually exactly the same as parts per million, except instead of multiplying by 1,000,000, we multiply by 100. And so again, the emphasis is not on the units, it is on the context. We need to make sure that we are plugging in for solute and solution, and not solute over solvent. And we see that very clearly in our first example. 80 grams of sodium hydroxide in 500 grams of water does not get set up this way. Because again, water is not the solution. When we go to plug this into the formula correctly, we're actually going to need to add the 80 back into it. Because solute plus solvent equals solution. The 80 divided by 580 times 100 is going to give us our 13.79%, and that's our answer there. Again, careful attention needs to be paid to the context of the things that they are giving and asking us for. In this second problem, how many grams of solute are in 800 grams of a 25% by mass solution? So we know 800 grams of solution, and so we don't need to do any funky addition. And when we plug in here, we get x over 800 equals 25. And to solve out for x, we can do any number of different algebraic approaches, right? But we are going to end up with x being 200 grams. Divide by 100, multiply by 800, or multiply by 800 over 100, or just multiply by 8 if you combine like terms and simplify out. Our last example is actually the trickiest of the bunch. They give you almost the same pieces as before. They give you 85 grams of solute. They tell you 40% by mass, and they ask you how much water you need. So when I put an x down here and I solve out, to get 212.5 grams, Is that the answer to this question? $212.5 is not the answer to this question because this x is the mass of the solution. And like we said before, solute plus solvent equals solution. And they are asking us for the solvent. So we know the solution is 212.5. We know the solute is 85. And so we actually need to do a little subtraction to solve for x, where we get the right answer of 127.5. Subtracting the 85 from the thing we solved for. And when we look at our answers here, they are going to line up nicely with what we solved for. It's important to remember, for percent by mass and parts per million, the context is the important thing. Making sure you're not accidentally putting water where solution goes. For molarity, the units are the more important thing. You need moles over liters to be able to plug in for molarity. Very rarely are you ever going to have a situation where water or solution makes a difference here. Because the only thing that is measured in our liters is going to be our liquid component. Right? I'm not going to measure how much solid I added in liters. To wrap us up for the day, let's look at one multiple choice practice problem. What's the concentration of a solution of 10 moles of copper nitrate in 5 liters of solution? Here we're looking at molarity, which means our units are the important thing. They hand to us on this silver platter moles and liters, and so we can just do our nice division to get 2 capital M, 2 molar solution. And with that, I'm actually going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.